From charged particles to mathematical elegance, discover how the Rutherford impact parameter reveals the core of atomic interactions. Now, many of you may know about Rutherford scattering from the gold foil experiment, where a heavy nucleus was stationary and alpha particles were set down a track and then deferred and deflected on hyperbolic trajectories. Today, we'll go ahead and dig up what this scattering parameter is. All right, so in the start of a new chapter, now that we're back in the book, we're back to chapter 10, which is a lot different than what we had seen previously, and it actually starts off with quite a bit of classical mechanics and classical scattering theory and wave analysis. But here we have a great example of how the two interact with Rutherford's scattering and his experiment. And in this problem, an incident particle of charge Q1 and kinetic energy E, keep this in mind because it'll come back again very soon, scatters off of a heavy stationary particle of charge Q2. A. Derive the formula relating the impact parameter to the scattering angle. Very important. Part B. Determine the differential cross scattering or the differential scattering cross section. Part C, show that the total cross-section for the Rutherford scattering is infinite, and let's try to keep in mind what that would mean. So, why do we care? Well, clearly, we like that we had the discovery of the atomic nucleus. It wasn't just the J.J. Thomson plum pudding model, but rather that in order to have these deflections, you had to have something really solid at the center and not just anywhere else where you didn't have the same interference. So the challenge for you is, well, Rutherford's model raised questions that couldn't be explained by classical physics. What were these questions? And of course, this is a long, hefty problem, so be prepared for a long video. And if you want the PDF with all the extra nitty-gritty on the math, please comment below and I'll send you a link to it and you'll be good to go. If not, just enjoy the video like old times. That being said, if you find value in this content, you can make a big difference by liking, subscribing, sharing it with a friend, or if you're feeling really generous, donating to help these curiosities keep coming out. Your support means the world to me and helps keeps this journey going. So with that, let's jump in. All right. Stop one on this journey before we actually get into the Rutherford model is let's take a look at the example from the book, utilizing some results that we see here for the Rutherford scattering case. Example 10.1 covers the elastic case of hard sphere scattering. And in this case, we suppose that a target, such as a billiard ball, which we see over here, big sphere, of radius big R, and an incident particle is a BB, which would bounce off elastically. So let's dive into what this would actually look like. So I'm coming in from somewhere and I hit this and I ricochet off. So elastic scattering. This alpha, which is going to be where I impact, which is related to this alpha to the horizontal, that is the incoming angle. And then what we're going to see is that angle of incidence, angle of reflection. We're going to have the same outgoing angle as well. Okay, so keep these two things in mind because when we get to the particle that's a charged particle instead of a BB, we're going to have to use the same argument here. And so what we say here is that the angle over here, theta, is the scattering angle. Now, one thing to note about all of these is that this makes a horizontal line. And in a horizontal line, we know we have 180 degrees. So all three of these angles have to add to 180, or pi radians. That being said, in this case, geometry alone is enough to relate the scattering angle with the impact parameter, which is b. So that tells us how far above that we're flying in from, and that's what's going to determine the trajectory. And as we see here, if we draw a leg down as if we're completing this triangle here, this is just the leg of the triangle, which would be b equals r sine theta, or sine alpha in this case. So keep this diagram in mind as we get into the analytic side of it. So, as stated, we see here that that horizontal line for the angles all had to sum to 180 degrees or pi. And we saw that we had an incoming angle that was equal to the outgoing angle. So we had two alpha angles and then plus theta. So either we could solve this thing for theta or solve it for alpha. Clearly both are nice, and this result is what we will use later. So keep that in mind as we're running through this. In fact, let's go ahead and circle it. This we will need later. Okay. This allows us to relate theta, the scattering angle, with the impact parameter because we solved for alpha and substituted it in. It's that leg of the triangle. And of course, we could use some difference identities here, and cosine of pi over 2 goes to 0. So that's not too bad. And then sine of pi over 2 goes to 1. So we're left with r cosine theta over 2. And then if we want to solve this thing for theta, the scattering angle, all we have to do is algebra. Divide over the r, take the inverse, and then multiply by 2. And then we see what we have here. So let's note here that the normal line to the surface creates the angle sectors that we saw in the diagram. So that angle sector that we see, that's going to be what we call the major axis when we get to the other case for Rutherford scattering. And so now we're actually pretty good. But one thing to note here is that this assumes that the impact parameter is actually within the scope of the billiard ball. Translation, that B is less than the radius of the billiard ball. If B is larger than the billiard ball's radius, there will be no collision, and the BB would fly straight over the billiard ball, and the scattering angle would be summarized as this piecewise function. No scattering because it would fly straight over, no deflection. If we're inside the radius, then we're going to have some deflection angle mimicked by the impact parameter and the radius of the billiard ball. So, this example is pretty straightforward, but there are cases where geometry alone just isn't enough to determine the impact parameter and the scattering angle. And for this, we're going to have to use something else. So let's go take a look at what's next. So this leads us straight to stop number 2. All right, so in this case, we have charged particles, and Coulomb's force plays a significant role, which of course is influenced by the inverse square law, and that's what the field strengths are going to dictate off of. So out here where R is big, the forces are going to be small. As we approach, as you see Q1's on this hyperbolic path, Q1's going to get closer and closer to Q2, and that's where the R would be minimized, or what we call the abscess of the trajectory. And from that, what we see is that that's where the force is going to be largest. So we can't actually collide with it because they're going to be wanting to repulse one another, assuming they're like charges. And in that case, what we see here is that we deflect out on the trajectory. So clearly, geometry alone is not going to be enough in this case. We have phi, which of course is going to be the incoming angle. Then we'll have, of course, if we draw the major axis here, we'll have an outgoing angle, and then the scattering angle theta is here with the impact parameter b. So keep this in mind that we're going to have to use some different techniques, and in this case, conservation of energy, which was stated in the opening statement, is going to be the go-to. Okay, so although conservation of energy is always a great tool, a lot of times this can also be derived via the conservation of momentum, or forces in that case. But nonetheless, energy will be our go-to for this route. So here we have E equals the kinetic term plus the potential term, which we know is just the Coulomb potential. Our kinetic energy, 1/2 mv squared. And then, of course, Q1, Q2 over 4 pi epsilon naught, 1 over r. So we're good to go there. The difficult part here is going to have to come into account with velocity. Noticing that we're moving in two directions, we can have a case here where the velocity has, let me change colors. V itself is composed of two dimensions. So that would be Vx squared plus Vy squared. And putting this in dot notation would be x dot squared plus y dot squared. But again, as we see, we're dealing with a polar potential or spherical potential, something that is related in polar coordinates. So we're going to have to switch this velocity into polar planar coordinates. And that's what this mumbo jumbo of a mess is down here. And if you're interested about how to get this, right here, this is the velocity in polar coordinates. Well, go back to what the distinction was. We had x equal r cosine, y equal r sine. Take the time derivatives, and you get what you need. That, of course, is in the PDF, so if you want that for the velocity and every other thing, go check that out because it is very useful. Or if you've taken a classical mechanics course or something like that where you had to convert it, this should look familiar to you. But this alone, r dot is what we're used to. We don't know how the angular velocity is changing. Thankfully, we have another trick for that, thanks to conservation of angular momentum. So, with that, angular momentum here, we have to be careful about its definition and what we're trying to accomplish here. So, we could use I omega or substitute in I, we have, mvr, and then if we substitute in for v, we have omega r, so that gives us m omega r squared. But omega is nothing but the angular velocity, so phi dot. So solving this for phi dot, we get j over mr squared. Again, this little fella here, this definition will come back later, so I just went ahead and listed it all. So we go from mv to I omega, or mvr if we're taking like a cross product. And again, we have to see that the impact parameter is the 90-degree to the route that we're taking at some point, which will come back later, of course. But nonetheless, we have phi dot here, which is the angular momentum, and mass over r squared, so we can plug this into the energy equation. Upon doing so, we see that we get r squared and a factor of square here canceling, because remember, this was r squared phi dot squared, so everything for this had to be squared. So cancel, and we can simplify down. But now we're stuck with the situation where we're left with something that has to be handled. So we're going to put everything like this over here and really isolate on this r dot and r down here, and we'll see why in just a second. All right, so isolate everything, get everything to the other side, minus the potential over, divide by the mass, multiply by 2. Now we have r dot and r left alone. So we did this because what we want is to relate b to theta. Okay, and this is going to have to come from r and phi. And we know that phi is going to give us what we need for theta because of pi minus 2 phi, as we saw in the example in the opening. So now what we need to do is figure out a way to write r as a function of phi, not t. And thankfully, we can do this thanks to the chain rule. And if we let u equal 1 over r, then we know that r dot, being the time derivative of r, can be extrapolated with the chain rule. So we have dr du, du dphi, dphi dt. Okay, we know what dphi dt is. That's this phi dot, which we saw from angular momentum. So we have this not squared, so we're good there. Then we have here, if u is equal to 1 over r, then r would equal 1 over u. All we have to do is multiply, then divide. So what we see here is that the derivative would be negative 1 over u squared, du d phi, and that's what we're looking for. Now we have a function that relates du and d phi. But this is really a function relating r and phi. So cool. And then we see that u and u cancel, so we get rid of it. So now that we have this as r dot is equal to negative j over m du d phi, plug this back into this, and we turn ourselves into a nice differential equation that we can that we can work our way through. Notice that with the substitution of u, we have a u squared here instead of this r squared, so we're good to go. And then, we'll square this, that'll get rid of the negative. And then both of these terms will have a j squared m squared, so we'll go ahead and factor that out as well. So, as promised, we factored out the j squared m squared, leaving us with the differential du d phi squared plus u squared. And of course, that's equal to all the other constants that we had. Again, we replace the 1 over r with the u, so that's where we get that from. And now, of course, we're going to have to solve for du dphi, and in doing so, we multiply over by the reciprocal of this bad boy, and that gives us a factor of m canceling, and then we minus this u over, take the square root, and now we're in a place where we have a what we want to be related, which is u via r, and d phi for theta. So now we're in a great position. And this turns us into a separable differential equation. Okay? Although this is not necessarily pretty, but it's still separable. So, to find phi then, what we would need is to integrate out, and of course that will come with some weirdness as we try to find the limits on the integral, but we're still good to go. And as we saw by covering the hard sphere example, we see that the approach angle alpha now goes to phi, and the leaving angle alpha goes to phi as well, but they're the same. So the scattering angle theta is just the difference from pi. So theta equals pi minus 2 times phi, but phi is this gross thing here. So now our task is, well, first let's look at a diagram to help us. We have here, again, the major axis here. That's what I was telling you about on the opening picture of this schematic from the abbreviated version. We have phi here, which would sweep again. We're looking at this as if it's a whole angle here, but nonetheless, when we split it up via the minor axis or major axis here, we get phi and phi here and theta here. So the geometry of Rutherford's scattering formula based on a diagram from his 1911 paper, the alpha particle is the green dot and moves along the red path, which is a hyperbola with O as its center and S as the external focus. The atomic nucleus is located at S, as we see in the diagram. A is the apsis, so the closest approach, which will definitely come. This is going to be very important here soon. B is the impact parameter, as we've had with all the others. And we see that what we're looking at is the trajectory or the deflection, so theta is still the scattering. So since, bring back that diagram. Well, since Q1 is starting out way to the left in that diagram, what we say is that that looks like R equals infinity. Okay, we're not actually going to get infinity, but we're looking at behaviors here, right? So with that, we observe that if we plug in infinity into our substitution, u of infinity would be 1 over infinity, which goes to 0. Cool. And that angle would be approximately phi equals 0. Of course, it's not going to be actually 0, but again, if we're looking at general behaviors, we're not going to have much of any angle to approach as we get infinitely far away. And the point of closest approach, that's what we saw as the apsis, which was r sub a in the diagram. And here, that would be the minimum r. And if this r is minimum, knowing that the u is 1 over r, if this is small, this means that this u is the max. And that's what we're going to have to use as our boundaries for the integral here. So let's put that together in the next slide. All right. So theta equals pi minus 2, and then we see that we have u equals 0 from at infinity, and u max, well, this is equal to r minimum. So you could flip it if you wanted to and just do, infinity and R max or R min. But again, you're going to get the same results. Here we have du over this nasty thing, which we'll call I as a function of u. And now we can actually break this down. But how we break this down is what we're going to need a little algebraic manipulation with. And since we observe that this thing here in the radical is a quadratic constant term, linear term, quadratic term. This tells us that this could theoretically be factored, and we have u minus u1 and then u2 minus u, where u1 and u2 are the roots. Okay? And the reason why we want to use this as the moment or the way forward is because recall that du d phi was equal to square root of 1 over or I of u. And from that, we know that the first derivative would tell us that u max has to be one of the roots thanks to this here. Set that equal to 0, it has to be a root. So if this is our game plan now, all we have to do is set one of these roots greater than one another. So by setting u2 greater than u1, we're defining u max to be the second root. And that's nothing more than just manipulating algebra and using the fact that a quadratic has roots, so we're good. And of course, we're going to have to find them later, but at least this will allow us to find an integral table to deliver an antiderivative for this that we can evaluate from u2 and 0. And that is what we'll do next. Awesome. So now that we're here, we can find an antiderivative and chug away at it. The antiderivative in this case would be negative sign inverse. Of course, it has to be a trig function with a square root and squares in them. So just be aware of that. If you remember trig sub, this is where you'll find that. But this gives us negative 2u plus u1 plus u2 over u2 minus u1. And of course, it's a minus outside, so the negative from the angle summation turns to a positive. And then now we have to evaluate at the bounds. So plugging in u2, we get cancel. One of these factors cancels with that. That 2 goes away. And then we see that we're left with a negative u2 plus u1. So we could factor out a negative, and that gives us u2 minus u1, but that's the same as what we had in the denominator, so they cancel. Beautiful. This, unfortunately, is just going to have to stay put for now. But we know that by canceling this, we're left with the sign inverse of negative 1, which brings us to a negative pi over 2. Now from there, what we see is that upon distributing the 2, this 2 and that 2 cancel, and then this pi is now negative, and that'll cancel with this pi, and this we're left with a 2 and this nasty thing here. So we have successfully found the scattering angle as a function of the roots. So nice simplified here, but of course, what does this mean? We're still not in our appropriate units or appropriate substitutions, so we still have to find the roots. And to do this, as Q1 is on its way in, because remember in the opening statement they said had velocity or had energy E. Okay, so that would tell us that with the incoming velocity V, again, R equals infinity, we see that the potential term here being 1 over R goes to 0. So get rid of that. And so we have something here that we can relate the energy with the velocity. So solve this for V squared. We get V squared equals 2E over M. Not bad there. But remember, we also used angular momentum. And here comes back our friend, J equal mvb. B is the perpendicular length at infinity. So of course, if we want P cross B in sine theta would be 1 because it's 90 degrees. This is why we use that. Okay, so now we can relate the angular momentum with the impact parameter, and we're good to go. But we have a v squared here, so let's put this and square this angular momentum. Square, square, square. Now I can put in a v squared here. In doing so, I get m and m cancel, so one of these factors goes by, and I have a 2mb squared e. Now, I'm in a perfect position to plug this into the radical quadratic expression, and that was equal to negative u squared, to put it in the form of the quadratic in standard form. And then here I had, of course, j squared in the bottom, so I go ahead and plug in our substitution in the linear term and the constant term. And as you see, we get a whole host of cancellations. Cancel, 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 cancel. And now this is going to turn us into a pretty nice quadratic equation that we can use the quadratic formula for. And as you see, we have after all the cancellations, we simplify nicely. So what we're going to do now is let everything that's a constant here, that has nothing to do with what we want, in this case, the impact parameter and R, but R again is related to U via 1 over R. So here, this is what we simplify to. Negative U squared minus a over b squared u plus 1 over b squared. And from here, if we want the roots, we have to set this radical equation equal to 0. And we notice that here I marked everything in red for the signs because we're going to factor out a negative. And setting it equal to 0, that negative is going to cancel. So we're left with our quadratic equation the way we like it. So from here, we have our constant coefficient a, b, c for the quadratic equation, and we just plug it in. From here, it's just a matter of algebra and work its way down. All of the work is in the PDF if you want it, but here we get a nice cancel cancel. If we find a common denominator here to match this one here, in this case we're trying to put a b to the fourth in there, and an a squared to have a factorable thing. So we need to multiply by a squared over b squared, top and bottom. And from that, we were able to factor out an a squared b to the fourth, and that leaves us with a 1 here and everything else that remains there. That will allow us to split this up and factor out another thing there and simplify further. So we're after factoring the a squared b to the fourth in the radical, we can take this outside the radical now, we're good to go. But we can also reduce this 2ba into a square instead of a 4b squared a squared. Now you see that we have an ab squared here and here, so we can factor that out. Put this with the 2 there. We see we have a big factor out front of a over 2b squared with -1 plus or minus the square root. Now, since we made it the case where u2 was greater than u1 with the roots for this case, especially when we're finding the integral limits, we see here that u1 has to take the negative sign and u2 has to take the positive sign. Okay, so this now allows us to relate the impact parameter to the scattering angle in terms of everything we wanted, theta and b. Now we just have to go ahead and plug it into the scattering angle that we found from the integral simplification and now tidy all of this up. Okay, so we plug in the roots u1, u2, u2 minus u1. All of them have the same constant, and with this plus minus difference, we're going to get some cancellations. So let's get to it. All right, factor out the a over 2b constants, top and bottom, cancel, cancel. Inside, we see that this negative radical cancels with this positive radical. This -1 cancels with this now positive one since we had to distribute that minus sign, and we're good to go. This brings us down to a simplification of -1, -1 gives us -2, and then we have square root, so we have 2 of them. So inside the arc sign, we have 2 and 2 cancel, and because arc sign is an odd function, we know that the negative inside and outside can go through and they'll cancel one another as well. So we successfully get theta equals 2 sine inverse of 1 over this square root. Now, since we're trying to find the expression for the impact parameter in terms of the scattering angle, all we have to do is uncover the impact parameter with algebra. So go ahead, divide over by 2, take the sign of both sides. Of course, we're augmenting this to where all the domains are happy, although this is not a math class, it's physics, so we're just going to assume it works. And if we see the need for extraneous solutions, then we'll point it out. But for here, we just now have to go ahead and finally simplify this by reciprocating both sides. So after taking a reciprocal of both sides, we get the square root up top, sine of theta over 2 on the bottom, and now of course squaring both sides. 1 squared is 1, we just put the square there, and we see we have uncovered, almost fully uncovered the 2b over a squared. So now we just have to minus 1 to both sides, which we see here. But this 1 needs to be with a common denominator with this sine squared. So we get a sine squared over sine squared, and that allows us to combine these fractions. So that's what this sine squared represents, is the common denominator for this 1. Thankfully, Pythagorean identity comes in clutch, and we know that this is equal to cosine squared. So we have cosine squared over sine squared. That leads us straight to cotangent, and that simplifies our work quite a bit. Thus, if we're trying to uncover the b, we have to take the square root, but since both are squares, we just know we have 2b over a equal cotangent. Now solving this thing for b, multiply by a, divide by 2. But remember, a is what we substituted out originally for all the constants that didn't have to deal with the impact parameter. So we have q1, q2, e 4 pi epsilon naught over 2. Combine that down. We have successfully found the impact parameter as a function of the scattering angle. And that was a wonderful journey and a whole lot of work and a whole lot of running around. In the PDF, I attached several resources for finding out where to look if you wanted to use conservation of momentum instead, and you get the same result. So that's a wonderful, nice setup. There's a couple other really cool methods too that I think were used from StatMech, but again, I have all those referenced in the PDF. But we see here, all that work to have something that's nice and neat, that's pretty darn cool. Q1, Q2 over 8 pi epsilon naught E with the energy that we have, that's pretty awesome. So, now that we have this, the rest of the problem is going to be quick and easy. Let's get to it. Stop 3 comes in when we want to find the differential scattering cross-section. To do this d of theta, we have to use equation 10.4, which of course was b over sine theta and then times dB theta in the absolute value. So we see here that our b term, we found that last page, and then the sine term was part of the derivation of this. Everything here for dB d theta, the derivative stays constant. The only thing that changes is this, and that's where we see that we have a chain rule effect, so negative of course. But with all that being said, this simplifies down a lot better than you may think. Remember that cotangent was cosine over sine. Here, here we have sine as theta, but we could use the double angle or half angle identity to put this sine theta in terms of a theta over 2. So with it, we have a factor of 2 out front, and we have that sine theta over 2, cosine theta over 2. Well, clearly, as you see, this cosine and that cosine cancel. This sine and this sine will combine. And as we see here, we have the absolute value after we clean this up of all the constants, but the 8 turns to a 16. And then we'll see that we have a sine squared there too. The negative sign will go away thanks to the absolute value, and we'll be good to go. So what we notice here is Q1, Q2, they're in both of them. That 8 and 2 from the half angle identities give us a 16. And the pi epsilon naught E stays consistent in both. Now, as I said, the sine from the double angle or half angle and the sine from the cotangent combine to a square. Since we have duplicate things here, that just gives us the differential cross section with the square up top. Again, that was pretty easy, all things considered. So that brings us to the total cross section now, where we have to integrate this differential cross section. And that's due to 10.7, where we see we have they represent a single integral, but we know that that single integral has to be a 2 integral because it's the d omega here's all the angles. This is called the solid angle. And so with that, we have to go ahead and use the polar coordinates again, since we got rid of r in the finding out the impact parameter, so we're good to go. So let's go ahead and set this integral up, evaluate it, and see what happens. Awesome. So we know that phi takes on 0 to 2 pi, theta takes on 0 to pi. We have a whole host of constants here. Again, squaring it. Here we just took the sine out, but since it was sine squared squared, that's why we have a 4 over there. And this will go ahead and put us to a, thanks to Fubini's theorem, the arguments don't need anything. We're multiplying inside so we can split the integral. This 2 pi comes from our phi, so we're good. And here, all the constants, no big deal. But we're stuck with this incredibly ugly looking integral, which is sine theta over sine to the 4th theta over 2. It's just not nice. So graphically, we can observe some things. Let's go ahead and pull up a graph. What this tells us is that the red line is the integrand. Okay, here is a vertical line where x equals pi. Here's a vertical line where x equals 0. And as we see, it's not going to lead to anything finite as far as area is concerned because this side shoots up to infinity at asymptotes. So with that, we're going to have to be aware that this cross section, total cross section, is going to be infinite just on the graphic side alone. So we see that as the integrand tends to theta goes to 0, this just doesn't work. We saw it went to infinity, and this is supported analytically, and we know that we can use a small angle approximation near theta equals 0, in which case, woo, I like that animation. In which case, sine of theta is approximately theta, and sine of theta over 2 is approximately theta over 2. Again, just Taylor series it out, only keep the first term. So the integral now looks like 0 to some really small thing that we'll have to take the limit of. This is improper, but of course I'm lazy. I'm not using all the notation for it. That being said, plug that in. You see that theta cancels with one of these. 16 comes out front from the theta over 2 to the 4th power divided by a fraction multiplied by the reciprocal. So that's where the 16 comes. Now we're left with a 1 over theta cubed, which is theta to the negative 3 power. The antiderivative brings us to negative 1 over 2 theta to the negative 2 power, but we just put it down there. And as you see, evaluating it from epsilon to 0, we have a 1 over 0, which tends to infinity. So the equal sign here should take with some hesitancy. But with that infinity there, there's no way that we can go ahead and state that the total cross section doesn't just keep going over. And we have the cross section there. But what I found interesting, and I believe this was from a Wikipedia page, these are all the hyperbolic trajectories that we saw from the gold foil experiment. So that's pretty darn cool how we see that when the impact parameter is pretty small, we get trying to get a head-on collision, we bounce back at a really stark angle. So we see that that is a huge scattering angle. Here, a little bit higher, not much higher, but a little bit higher, we get another angle deflection that's pretty big. I was not expecting to see a 90-degree here, but that was pretty cool. What we had in the diagram is more of the green or the orange here. And then, of course, if your impact parameter is huge, you're relying solely on the fact that the Coulombic force is pushing you away, so you're only deflected at 12 degrees. But nonetheless, I thought this was pretty cool and enlightening. So that was a journey. But nonetheless, Rutherford, your work has definitely helped us quite a bit. Oh, hey. That was quite an endeavor, and I'm glad if you listen this far, I'm glad you've listened to it all. Uh, there were so many ways to start the problem, but I felt it necessary to go over the example with the classical side of things and see how that's not always going to transcend. Geometry is not always going to work only. We have to have the other things like momentum, energy, although they're related, you know, those techniques are not going to run away from us. So, in summary, you saw quite a bit of technique and mathematical manipulation that had to be put in there in order to find a route to solve this. There are several resources out there, but I haven't seen one that was quite complete in my mind. So if you do see one, please send a link for it so I can put it in a PDF and repost it because this thing is well known. It's been talked about in every physics book that I can think of. So very, very important that we talk about it. Um, that being said, first off, welcome Jeffrey. I appreciate your support and every other patron that we have. You just joined, so very much thank you, thank you, thank you. I hope that we can connect and talk about physics and some of the other new stuff like everyone else I've tried to. Um, that being said, this this channel and this work does not work without the supporters. So please understand, I appreciate you all, and I'm looking forward to keep growing with you and doing some more stuff that are going to be bigger side projects after I get through the couple books that I wanted to. To me, it's really important that we have a foundation on everything before we start tinkering with how these foundations unite together. And that's what's going to be the fun exploration part of this process. So, if you're interested in that project, it's a long term project and the support will be needed. So, if you're interested in that, please consider either donating through Buy Me a Coffee or joining the Patreon page where you can have access to all the other fun stuff and supplemental materials, the projects, and one on one help. New content is posted weekly, especially again as the new semester is coming up. There's going to be a lot of things to look over. So please be aware, help is there if you want it. Books, notes, and other reference materials are either found below or in a PDF because these problems are getting too dense to do in just one foul swoop. So be aware they are available. If you have any questions, please feel free to reach out. And as always, thank you for watching. Until next time, stay curious.